Balchem Animal Nutrition and Health, we strive every day to deliver results you can see in your animal's productivity and your bottom line. From a smooth transition into the milking string for your fresh cows, to a happy welcome home from your furry friend. From a strong start in your poultry flock, to consistent weight gains for your finishing hogs. We expect to earn your business and your trust with our people, our products, and our science. Our people have an intense passion for your animals and your success. You can count on us for honest, candid advice and practical solutions for your toughest challenges. As the global leader in choline production, chelation, and encapsulation technology, we take our obligation to you and to the environment seriously. Our products are backed by the most extensive and thorough research portfolio, while our business is committed to advancing environmental sustainability and animal welfare. In the end, it all comes down to results. Balchem delivers real results you can count on, results that exceed your expectations, and results that bring true value to your bottom line. Leading the charge to meet the nutritional needs of ruminants, monogastrics, and companion animals, Balchem offers a growing portfolio of nutritional products and a dedication to innovation and industry sustainability. Balchem is here to solve today and shape tomorrow. As the global leader in choline, Balchem has spent more than 50 years perfecting the art and science of choline chloride production. The new Puricol line delivers the highest standards of quality, produced in state-of-the-art manufacturing facilities, and backed by the strictest process controls for a level of purity, safety, and consistency you can't find anywhere else. Turn to Puricol choline chloride from Balchem for an unmatched level of quality you can trust. Visit balchemanh.com to learn more. Good morning, everyone. My name is Kim Jones, part of the marketing team for Balchem, and welcome to the Real Science Lecture Series. Protein is vital to every animal and especially important in swine and poultry diets. In today's Real Science webinar, the impact of thermal processing on protein quality and monogastric nutrition, Dr. Chad Paulk from Kansas State University will walk through some of the newest findings around processing and how that impacts quality and availability of protein and amino acids in the diet. Dr. Paulk is an associate professor of feed science and management in the Department of Grain Science and Industry at Kansas State University. He received his bachelor's degree from the University of Georgia and his master's and PhD degrees from Kansas State University. He previously served as an assistant professor of swine nutrition and production at Texas A&M University in the Department of Animal Science from 2014 to 2017. His current responsibilities include 60% research and 40% teaching. His three main areas of research include feed processing, feed safety, and monogastric nutrition. Dr. Paulk is responsible for teaching classes pertaining to qualities of feed ingredients, animal food safety, and an introduction to grain science. Chad, you should now have control of the screen.
Alrighty, thank you for that introduction. And as she mentioned this morning, my roles here at Kansas State are with the feed science program, and we do a lot with ingredient and final feed quality. And so over the past couple of years with some of our research as well as some of my teaching responsibilities, I've generated a couple of questions, and I kind of wanted to share the data with you today that led me to those questions, and hopefully will help lead you to learn some new things, but also maybe you can help me learn a couple of things as well. So what really came about throughout my last couple of years is thinking about the how is thermal processing utilized in the livestock industry on the feed side? And there's really two main areas. It's either going to be for ingredient processing. I think the most Familiar process we have, at least here in the US, is the heat processing with soybean meal. As we go from the oil extraction of the soybean to our thermal processing, they end up with soybean meal. And then also in the pelleting process, where we're adding that steam, getting moisture and heat through this pelleting process. And so there's a lot of questions on, do these processes benefit protein utilization, which typically we think about they do, but then can you also apply too much heat or too much moisture and denature those? So really, as a feed scientist and a nutritionist, our common goal is to figure out what's the balance. How do we optimize the nutritional quality of these ingredients or the final feed product through thermal processing, and what tools are available for us to make decisions for these processes as well. So what I'm going to do today is, first we're going to talk about ingredient processing, and I'm not here to pick on soybean meal. I think soybean meal is also a great ingredient. We've really figured out the process. We can utilize those amino acids within that soybean meal, but there is a lot of data on thermal processing, QA measurements of soybean meal. So it's really a great example to talk about how do we measure protein quality, how does thermal processing influence protein quality. So I'm going to use soybean meal as the example today, just to talk about some different things and also ask some questions. And then we'll follow up with the pelleting process. You know, traditionally we think about increasing conditioning temperature. If we maximize our conditioning temperature, we're going to improve pellet quality. This optimizes our response to pelleting in both broilers and on the pig side of things. And so sort of raise some questions there with some of the changes we've seen in the diet formulation, as well as maximizing these conditioning temperatures either for pellet quality or for microbial control. Is there potential to reduce amino acid availability? So those are really the main two things I'm going to discuss today. And kind of just to start out with a little introduction, I want to take a step back and think about, okay, how does thermal processing potentially influence protein quality? And so the first thing, as we apply this heat and this moisture, we start to denature these proteins, or essentially they start to unfold. And initially you think, okay, this will allow us to have enzymes to have more access to these proteins, make these amino acids that are within the proteins more available to the animal. This reaction is typically irreversible, and it is accelerated by moisture. So not only does heat is the main factor in this, but also the moisture content. So it's going to be a balance of these two things. There are also other things such as organic solvents, acids, bases, which would be the pH, and shear that occur during these processes, depending on how you're thermal processing these ingredients or complete feed, that can influence the protein quality as well. Some of the consequences are, one's loss of enzyme activity. I'm not going to talk about this today, but especially with the widespread use of phytase in diets, this is a very important topic, phytase stability during the pelleting process, especially as we chase pellet quality. So anything I do to improve pellet quality, 9 times out of 10 is potentially going to have a negative impact on enzyme stability or activity. And so trying to find that balance between the two is an important topic, but that's for another day. Also, there could be microbial control or toxin destruction with thermal processing, improved digestibility, as we talked about, losses, solubility, or textural changes. So that comes into some of what I think about as pellet quality. So just the age-old scheme of, as we increase our thermal processing, especially on ingredients, we kind of have this digestibility curve of where, as we're destroying anti-nutritional factors, potentially unfolding some of those proteins, we see an increase in our amino acid digestibility. But that is up to a certain point, and then we potentially start to bind some of these amino acids. And the main one we're going to talk about today is lysine, and I'll explain why in a minute. But then, yeah, after you overheat or apply too much thermal processing, you start to reduce that amino acid digestibility or that lysine digestibility. So our goal in thermal processing is how do we optimize this process to maximize digestibility, to maximize ingredient utilization. And so when we think about the over processing, or if we put too much heat on these ingredients, we start to get the Maillard or the browning reaction. And essentially what you have is glucose or reducing sugar that's going to bind with the free amine group on your amino acids. So lysine is typically the amino acid that we start to lose digestibility of first, and that's because it has this extra or this free amine group that's going to bind to your reducing sugar. And so then we go from having a glucose and a lysine residue to what we call a Schiff's base. Okay, and so a Schiff's base is kind of our intermediate compound, and so at this point, our lysine, our total lysine that is being analyzed can still be detected. However, it's not absorbed by monogastrics. And then if we continue to have over processing or more heat applied, then we get these amidori compounds, okay? And after these amidori compounds, we start to have release of these pre-melanoidins as well as these melanoidins in this reaction. And so at this point, if we end up with amidori compounds, the lysine is not detected. So you can't, your total lysine, essentially, if you were looking at total lysine analysis and you ended up with more of these amidori compounds, you'll actually see a drop in your lysine analysis. This is also not going to be absorbed by the animal and utilized. So when we think about this from a QA standpoint and how do we measure this, it kind of gets a little tricky, because if we have too much thermal processing to a great extent, we can see it in a reduction of our total lysine. However, if we're kind of at that intermediate stage of maybe we're starting to get too much thermal processing, but it's not to a great extent, how do we detect that? Is it going to make a difference on the animal's performance? You know, what's the importance of that? So, you know, if something is extremely over processed, we can detect it. We know there's going to be a difference, but it's some of those small minor differences that are harder to detect. And so this is a multifactorial response. You know, it would be nice to say if you're at this temperature, this moisture, everything's going to be fine. If you exceed it, it's not. So we could predict things, but there's a lot of factors that play into it. And Dr. Stein's group has demonstrated this on the swine side with a couple of different data sets. But just to kind of summarize it real quick, they did a digestibility study, amino acids, looking at lysine digestibility with DDGs. And they reduced that lysine digestibility when oven drying at 100 degrees C, okay? And so oven drying doesn't have that moisture component, so it's even, you know, that's one factor that wasn't even a part of this, but they still reduce the digestibility, where when they oven dried soybean meal at 125 degrees C for 30 minutes, there was no effective drying temperature. And so the conclusion was, you know, some of these differences could be associated with the composition of DDGs and the availability of those sugars to actually bind the lysine, as we just showed in the previous slide. So with soybean meal not having as much of those sugars, very minimum amounts, the Maillard reaction didn't take place at 125 C for 30 minutes when oven dried. However, you'll see in the next couple of data sets, when they do this in an autoclave, which has moisture and pressure and temperature, then you start to reduce the digestibility of lysine. And so we have to figure out, okay, what's causing this heat damage and how does it vary? It's going to vary depending on your ingredient, the composition of those ingredients, your final temperature you hit, the moisture content or the water activity, pressure can influence it, as well as pH. And so from a nutritionist standpoint or purchasing ingredients, thinking about, okay, how do we determine if these have been over processed or had too much of heat applied to them or not. How do we make purchasing decisions or adjustments in our diet formulation? What can we measure? And so traditionally, Dr. Parsons' group, really utilized this protein dispersibility index. And so remember, we have this, you need enough heat to destroy your anti-nutritional factors. In soybean meal, what we're concerned with the most are your urease and trypsin inhibitor. And so how do we apply enough heat to reduce those, but then also maintain or prevent the Maillard reaction from occurring to maintain that digestibility and lysine? And so this initial data set with the protein dispersibility index, you can see as they autoclaved these soy white flakes. So they used soy white flakes so that there was no prior heat processing. But as you autoclave those soy white flakes, you get a decrease in your protein dispersibility index, which really represents the decrease in your urease as well as the decrease in your trypsin inhibitor. So this is just showing it's an easier way. You're just looking at the solubility of those proteins in water. So it's a really easy, cheap measurement to do to give you an indication of, is this under processed or not? But this measurement didn't really, you can see here, they also measure KOH solubility. This is another measurement we look at to assess thermal processing if it's over or under processed. And you can see here, they only got down to 78%. So really, this just demonstrates the PDI as a good metric to determine if it was under processed or not. And it related to the bird's performance as well. There was a follow-up study, or this study actually was prior to, but this study was at the University of Georgia, and you can see they achieved more of a over-processing in this experiment on the soybean meal, with the KOH solubilities decreasing from 82 to 46, where in the previous study, they just got below 80% on the KOH solubilities. And so this study demonstrates how if you over-process that soybean meal, you can measure it with the KOH solubility, and it correlated with the performance of the birds as well. So once again, I want you to keep in mind, these studies were done using soybean meal or soy white flakes, but using an autoclave. So you have moisture, you have pressure, you have temperature, and it's demonstrating the ability of these QA metrics, PDI and KOH solubility, to estimate the quality of this protein and how it affects performance of the bird. But still, these are pretty, an autoclave is not something we're going to use in typical feed manufacturing processes. So it's something we need to keep in mind as we're improving, getting more precise on what we're trying to do with QA and decision-making processes. Another metric I really wanted to talk about was something Dr. Stein's group demonstrated on the pig side, but it's this lysine to crude protein ratio. So we discussed how as you have those amidori compounds, the browning reaction, you're going to reduce the total lysine that is analyzed, okay? However, your nitrogen isn't necessarily going anywhere, so your crude protein should stay consistent. So if we look at a lysine to crude protein ratio, this should be indicative of over-processing or a decrease in lysine. And I don't have the digestibility data here, but they did demonstrate a reduction in digestible lysine as your lysine to crude protein ratio on soybean meal decreased below 6. So they had autoclaved at 125 for 15 and 30 minutes. This decreased the lysine to crude protein ratio. They did the same temperature in an oven drying method, and notice how the lysine to crude protein ratio stayed above 6, and the digestible lysine values matched that as well. So there was no difference between the non-heat treated and the oven dried compared to the two autoclaved. And the main thing missing here is that moisture component. So if we're thinking about protein sources, in this example, soybean meal quality parameters, where has this data kind of led us as How do we compare different sources? How do we make purchasing decisions? What are things that need to be considered from a diagnostic tool if we think we're having some kind of issues on the farm? And kind of some rough estimates. If you look at different publications, these numbers may be a little bit higher, a little bit lower, but this is kind of where I ended up and how I think about things. But if you were going to send in a sample and have it analyzed, your protein dispersibility index should be between 15 to 30%, your KOH solubility between 78 and 84%, lysine to crude protein ratio above 6%, trypsin inhibitor at TIUs per gram 3,600 to 7,000, and then you want your delta pH for urease in that below 0.1 range. So once again, these are all for soybean meal. And so could you have similar metrics for distillers grains or other things of that nature? You could, but you need to understand kind of what the baseline is going to be like. Is your lysine to crude protein going to be different because of the expected amount of lysine compared to crude protein, et cetera? So this was a study I conducted as well to try to correlate some of these measurements we just talked about back to the digestibility of lysine. And so they took 22 different soybean meal samples, measured different things. I haven't talked about this up to this point. I'm just going to focus on protein today, but they did also look at things like NDF and your oligosaccharide content. But essentially what the authors determined was the KOH solubility was significant and correlated with the digestible lysine in these soybean meal samples. The second best correlation, but still not as good as the KOH solubility, was the reactive lysine. And so the reactive lysine is a method that's going to essentially try to determine, it goes through different processes, and I'm not going to get into the details of the different method, the different methods that could be used to measure reactive or available lysine. But it does try to simulate that digestibility of that lysine, what is actually available due to some processes within the lab. However, in this example, still our KOH solubility had a greater correlation than that of reactive lysine. But this reactive lysine is something we're continuing to learn about and figure out how it can be utilized and how it can be measured. So with that, we had an opportunity, thanks to the Illinois Soybean Association here at Kansas State, to look at different quality of soybean meals to understand how crude protein content of the soybean meal influences amino acid digestibility. But I actually, I guess lucky or unlucky, kind of discovered an alternative objective of well to learn about processing. And so the reason that is our control soybean meal here was sourced out of the Midwest from a commercial soybean facility. So they processed that soybean into soybean meal. And then we also, from that same region, sourced a soybean that hadn't been processed and sent it to a pilot scale crush facility, what we're calling experimentally processed, to have that soybean processed in the soybean meal. Okay, so this soybean, the soybeans from the 49 soybean meal and the control soybean meal are from the same region. We can't guarantee that they're exactly the same, but we're hoping that we did what we could to make them as consistent as possible. You can see that this soybean meal did have a higher crude protein content, but this can be associated to a higher dry matter content as well. If you put them on a dry matter basis, they're a lot more similar. Okay, we then also took two different varieties of soybeans from the Midwest as well. One that had a high crude protein content. Whoops. You can see we ended up at roughly 52% crude protein on the soybean meal versus 42% crude protein on the soybean meal. So our initial goal was to look at, okay, how does increasing crude protein content affect amino acid digestibility? But then we also had this internal control of commercially processed versus experimentally processed, because all 3 of these soybean meals were experimentally processed. When you look at our KOH solubilities, the 2 controls had very similar KOH solubilities. The 42 and the 52% crude protein soybean meal had actually a little bit lower KOH solubilities, but not very different between the 2. Also, trypsin inhibitor levels were within that acceptable range we just discussed, and our lysine to crude protein ratios were in that acceptable range as well. When we looked at the apparent ileal digestibility of lysine, so this was on broilers. Broilers were euthanized at day 18 and samples collected, so they were very young broilers. But when we looked at our digestibility, we actually saw a reduction in lysine digestibility in our soybean meal, our control soybean meal processed experimentally versus the control soybean meal. So there was something different in that commercial process. There could be other things too that we're not aware of, but assuming all of our controlled procedures were effective like we planned for them to be, the main difference here is the location of processing, which led to that 4% difference in amino and lysine digestibility. The other thing we did see was kind of what we expected, or some of the data shown with a relationship of crude protein and lysine digestibility. But as we increase the crude protein content, not only did we increase total lysine, but the digestibility of that lysine also decreased or increased. So our high protein soybean meal processed experimentally was similar to that of the control soybean meal, but the 2 control soybeans, the experimentally processed, actually had a decrease in digestibility compared to that processed commercially. So there's something going on with the processing there. But if I look at my QA metrics, the KOH solubility, lysine to crude protein ratio, nothing really gave me an indication that I should see these differences between these 2. You could argue the KOH was actually 10% lower, so that could potentially explain this. However, our high protein also had a lower KOH solubility, which had the best digestibility. So we then took this data, all of our digestible amino acid data that we gathered, we had the same soybean meal left over, and we formulated diets. So all of these diets, essentially, if our calculations were correct, should have had the same digestible amino acids provided to the animal. So we expected that we had different levels of soybean meal in the diet because of the different amounts of digestible amino acids provided. So really our hypothesis was that we formulated these based on digestible amino acids, therefore our growth performance should be flat. So we expected no difference in average daily gain or feed conversion ratio because of how we formulated those diets. What we found though was our control soybean meal birds, or birds fed the control soybean meal, actually had an increase in average daily gain. There was no difference between our experimentally processed soybean meals, which is what we expected. However, they were all less than that of the control soybean meal. And this was all driven by feed intake. So something within these experimentally processed soybean meal led to a decrease in average daily feed intake compared to that of the control soybean meal. When we looked at it on a feed conversion basis, there was no difference, and all birds had a similar feed conversion ratio. So if I look at my QA metrics, nothing really led me to believe that I should see the difference in the control soybean meal experimentally processed versus that processed at a commercial facility. However, there was a difference in lysine digestibility. And then when we actually formulated diets using those values and fed it to the birds to determine growth performance, something caused a decreased feed intake in all of our soybean meal sources, or the diets with our soybean meal sources that were experimentally processed. So, you know, at this point, I really don't have an answer of what's causing that. You know, we could hypothesize a lot of different things, potentially lead to other research. But if it is a thermal processing issue and it's something to do, you know, with that heat step, what we're measuring from a QA standpoint isn't picking up that difference. But even when we accounted for those differences in digestibilities of amino acids, it still led to a decrease in intake. So, you know, is there something else going on that I haven't measured or thought about that's driving these differences? Something with the process that could be influencing these intakes? You know, at this point, we don't know, but something definitely was different in the two processes that led to a difference in the bird's performance. So now I kind of want to shift gears. We talked about how do you measure QA on the protein side for ingredients, mainly focusing on soybean meal. I left you with that example of the differences in digestibilities and also how the process influenced bird intake as well as digestibility. Now I kind of want to shift to the pelleting side. This is where we really see thermal processing on the complete diet. You know, there may be other areas where you could experience thermal processing if you have an extruder or something like that, but this is by far the most common that we deal with, at least in the US, on the feed manufacturing side. And as you're aware, you know, we pellet diets to increase palatability, animal performance, feed handling characteristics. It reduces feed wastage, selective feeding, ingredient segregation, and also it can have a microbial control. And so within the pelleting process, we alter things such as our conditioning temperature, potentially steam pressure, how long our feed is in the conditioning process. The moisture content is going to depend on the initial moisture content of the feed as well as your steam addition, and then your dye parameters, your dye diameter, the hole diameter, as well as the dye thickness. And so as things have kind of changed in the US feed industry, depending on the price of corn and soybean meal, there's opportunities to increase some byproducts from the food industry or other places that have a higher sugar content. So remember, we talked about how important that is and how that leads to potential in the Maillard reaction. We've also seen an increase in pelleting temperature, whether it's for microbial control, pellet quality, whatever the reason is. We're trying to maximize our pelleting temperature to increase that quality, increase that microbial control. And as you increase that temperature, you're also adding more moisture via the steam. So we talked about all the things that can lead to the browning reaction, and the way some of our diet manufacturing's gone, we're actually increasing the potential in theory for that to happen. So as we add more sugars to the diet, as we increase the conditioning temperature, are we now pushing our pelleting process to cause us to reduce the digestibility of some of our amino acids? And I want to start off, West Virginia did a project asking this exact question and trying to determine, is this a factor in the broiler industry? Can you potentially influence amino acid digestibility with the pelleting process? And does that depend on your type of diets? So they had 3 different diet types. They did a 3x3 factorial. They had a corn soybean meal based diet, a basal diet with a different protein source, so they added meat and bone meal, and then they added 7.5% bakery byproduct. So bakery byproducts coming from the bakery industry should be adding a lot more of those reducing sugars to your diet, which could potentially lead to the binding of those amino acids. They had, for their processing factor, they had mash diets, pelleted diets, and then they actually double pelleted the diet as well. So it went through the pelleting process twice. They conditioned these diets at 90 degrees C. Their condition retention time was 10 seconds, and then they used a 4.5 or 4.7 by 44 millimeter dye. So you can see they measure digestible lysine concentration, and kind of as we've seen in previous data and as West Virginia has demonstrated in other data that they've generated on the broiler side, when you pellet that basal diet or that basal diet with meat and bone meal, you get an increase in digestible lysine concentration. So that pelleting process actually increased that digestible lysine. However, in their basal diet that had the bakery byproduct, their MASH diet had an increase in digestible lysine concentration than all other diets, but compared to this MASH, they did actually see a decrease in digestible lysine concentration when that diet was pelleted. So this was on broilers. This could lead us to believe, okay, when we add these sugars in here, we have these higher pelleting temperatures, 90 degrees C is going to be on the upper end of where we would pellet. Is there a potential to reduce this digestible lysine concentration? And based on this data set in the broiler side, this will tell us we need to be conscious of this and make sure we're keeping this in consideration if we have that bakery byproduct meal or those sugars that could come from somewhere else in the diet, and what the potential impact is. The other thing I kind of wanted to point out, this was some of their QA measures that they also reported in this study. So here's the digestible lysine concentration we just talked about. You can see this is that control diet with a bakery byproduct, and then the reduction in your digestible lysine concentration. They also measured available lysine, which once again, this is I think a new QA metric that we're trying to understand how to utilize. But in this experiment, you can see the difference in these three diets, in my mind, doesn't necessarily match up quite the same as what we're seeing in a digestible lysine concentration. So I think, we still have a lot to learn here, but from this study, it didn't quite have that correlation that we would expect to see. So key conclusions from the experiment out of West Virginia: pelleting and double pelleting did improve feed conversion ratio, and then also that digestible lysine concentration. However, that digestible lysine concentration did decrease when pelleting the bakery byproduct meal diets. So something to keep in mind. We had the opportunity here at Kansas State to run a very similar experiment on the swine side of things. We did a 2x2 factorial, so we also had mash and pellet diets. In addition to increasing the amount of sugars in the diet, which we did by adding distillers grains and bakery byproduct meal, we also did crystalline amino acid inclusions. So in the swine industry, we'll formulate a lot of diets, with lysine, methionine, threonine. We also have the opportunity now to include valine, isoleucine. And so thinking about, as we increase crystalline lysine, does that lead to an increase in the potential for the Maillard reaction or not? And that's something we wanted to test. So these are just examples of our diets here. You can see what we call our high reducing sugar diet. We added 20% distillers grain, 15% bakery meal. And then our high crystalline amino acid diets also went all the way to include, sorry, I forgot tryptophan as well. Tryptophan is utilized, but it includes tryptophan, valine, isoleucine, threonine, methionine, lysine. And our low crystalline amino acid diets, we still had, just for what we would consider industry practice on the low side, but we still had some lysine, threonine, and tryptophan in those diets, but not your methionine, valine, isoleucine. So when we pelleted these diets were fed in mash and pellet forms. Our goal was to be at 90 degrees C as well. However, our high reducing sugar diets, we started to have the dye would plug, so we had to back off. Our temperature, we still were picking up roughly 5 degrees across the pellet tie. So our hot pellet temps ended up being 89 to 85 degrees Celsius when pelleting these diets. And when we took the complete diet, so initially we talked about KOH solubility from a soybean meal standpoint, but we measured it on our complete diets. And the interesting thing is, when you look at our MASH diets for our low crystalline, our control diet, our high reducing sugar diet, and our high crystalline amino acid diet, when we pelleted those diets, we actually saw an increase in our KOH solubility in the pelleted versus MASH diets. So, you know, this kind of matches the broiler data we just saw. Okay, if I see these numbers, I'm thinking, well, I may potentially see an improvement in lysine digestibility in these pelleted diets. The interesting thing is, on our high reducing sugars, high crystalline amino acid diets, we actually see a decrease, roughly 8% decrease in KOH solubility. So based on the way we designed this experiment and looking at these numbers, I'm kind of starting to think, okay, maybe there is something here. And if you push this and have, you know, a lot of free lysine and a lot of your reducing sugars, can you potentially start to cause this browning reaction during the pelleting process and reduce that lysine digestibility? However, when we measured lysine digestibility, there was no interactive effects. So sorry, but this slide is all main effects. So we had no interaction. If those KOH values would have held true in correlation with the digestible lysine, we would have picked up that interaction and saw a decrease in that digestible lysine, but there was no difference, no interaction there. So we don't think, in terms from a digestible lysine perspective, if we were having that browning reaction, it wasn't enough to affect digestible lysine, and didn't cause the interaction on the digestible lysine standpoint. We did see an increase in amino acid digestibility in pelleted diets compared to the MASH diets. There was a tendency for an increase in lysine digestibility when we increase the amount of crystalline lysine in the diet. And our diets with high byproducts, the bakery mill, the distillers, had a decrease in lysine digestibility compared to our controlled diets as well. We did a similar study where we also measured growth performance. You know, this time we ended up, our conditioning and hot pellet temps were a tad bit higher, but roughly 90 to 89 degrees C. And then we measured growth performance on these animals. Once again, we did not pick up an interaction. We saw improvement in feed efficiency when we pelleted those diets versus MASH diets. Tendency for increase in feed efficiency when we fed high crystalline amino acid diets. So this is a very interesting response, because the pigs fed the high crystalline amino acid diets had an increase in feed intake, which led to this tendency for poor feed conversion here. And then also we had an improved feed conversion in our high reducing sugar diets. These pigs actually had a reduction in feed intake as well. So major conclusions, we saw our typical pelleting response. We saw improvement in amino acid digestibility when we pelleted those diets, but we didn't pick up any interactions that led us to believe that we're starting to increase that browning reaction to an extent that it's affecting digestibility of those amino acids. So between these two experiments, it seems like maybe on the broiler side, there is potential. It's something we need to think about. Even pushing the high sugar, the high free amino acid diets with high conditioning, hot pellet temperatures, we didn't pick up any differences. Doesn't seem to be a big of concern on the swine side. So to kind of conclude this presentation, we've talked about thermal processing on the ingredient side. We've talked about it in the pelleting side, the complete diet side. I want to just, you know, we've demonstrated how KOH solubility is utilized. Sometimes we can see differences in KOH solubility that are indicative of the quality of the ingredient. Other times we're picking up difference in performance, but our KOH solubility is not telling the story. We've had some opportunities here at K-State to do a couple new QA measurements that we've tested, and I just kind of wanted to bring those to light. We still have a long ways to go to understand, how do they actually correlate with digestibility? Are they a valuable tool? But something that we have been thinking about. So this is just to bring your attention back to the traditional methods. Remember, we had the protein dispersibility index, the protein solubility. And on this National Pork Board study that we completed, we actually attempted to measure the melanoidins. So remember, the melanoidins was the product coming off of that amidori compound in the browning reaction. And this is something, we have a colleague here at K-State that uses this measurement to determine the Maillard reaction within the baking process. And so we decided, hey, let's see if we can pick anything up. And we started by measuring just the complete ingredients. And you can see in our ingredients that go through a thermal processing step, soybean meal, distillers grains, bakery meal, had an increase in melanoidins compared to that of corn. There's other things to consider too. These also have a difference in protein content and other things. But those that do go through that processing step did have an increase in your melanoidin content. When we looked at our diet melanoidin content, once again, as we increase the amount of those byproducts in the diet that have gone through a thermal processing step, we see an increase in the absorbance values used to measure melanoidins. And then when you pelleted those high reducing sugar diets, we kind of see a further increase compared back to those mash diets. So once again, these are absorbance values. We're still trying to figure out, hey, does 12 versus 14, is that really a biological difference? What does that look like? How does the animal interpret that? But we did see these trends in an increase where our control diets, they were similar back to the control pelleted, were similar back to the control mash. But once again, we didn't necessarily, there wasn't any differences in SID lysine that could relate back to these minor differences. On our second set of experiments where we pelleted these diets for the growth performance study, we still see the increase in melanoidins in our high byproduct diets compared to our control diets, but we didn't see that increase in melanoidins in when we pelleted those diets versus the control diets. So, maybe those differences we tried to get excited about aren't really telling us, what we thought they were. Still a lot to learn here, but you can see when you do have that difference in protein and that increase, that processing, you are at least detecting some kind of differences. So we still have a lot to learn here, but the potential opportunity. The next thing I want to talk about is NIR. And so the available lysine, reactive lysine measurement we talked about is an expensive measurement. It also takes a decent amount of time to get measured. But we're fortunate enough that the NIR technology is making a lot of progress and coming a long ways. And there's now calibrations out there to use this NIR to measure available lysine. And so, trying to understand how we incorporate this and the value behind it is something we're working on. But I think there is a lot of opportunity. We had AB Vista funded this project and provided some calibrations to test and utilize NIR to measure reactive lysine and compare that back to available lysine that was measured on soy white flakes. And we did the available lysine measurement at the University of Missouri. The really cool thing about this was our correlation, our R-squared value between the two was highly correlated. So the reactive lysine measured using NIR was highly correlated to available lysine. The thing I will tell you that you need to be conscious of is our accuracy was off. You can see here we vastly underpredicted the reactive lysine. And this just comes back to how NIR works and making sure you're biasing your equations. Once again, these equations were based off of soybean meal measurements. They're calibrated using soybean meal. We autoclave soy white flakes. It had a lower lysine content than the average of the soybean meal. So there were differences here. But even with that, our correlation was high. We just need to come back, bias these equations to get our accuracy back where they need to be. But this is something you can work on and develop. Similar story when trying to measure lysine to crude protein ratio. And then we also looked at available lysine to total lysine. The only difference here is this is more of a quadratic shape, still highly correlated. The thing is, you can kind of see the linear function in these later lines, but we really overprocessed our low levels here on this percentage of reactive lysine to total lysine. So these samples were essentially black, and I don't think they're going to be very applicable to what you would see in the industry, or at least I hope not. But you can see we still have this more of a linear function in these samples that aren't quite as overprocessed. But the other interesting thing here is thinking about what's the value of looking at reactive lysine as a ratio to total lysine, and does that give us any more information and something to think about in the future. So with that, I'd be happy to take any questions. I really appreciate everybody in attendance today. I hope I brought some new things to light, or at least reminded you of some old things to think about. I do want to point out, if you go to our K-State website and then type in the feed science program, we are currently updating our research. We now have an annual research report that tries to get all this data out to feed manufacturers and nutritionists as soon as possible so that they can utilize it. We have data on feed processing, pet food processing, poultry and swine related topics as well. And we've also just updated, kind of similar to what we talked about today, we updated our QA resources. So there's a lot of documents. One of my students, Kara Dunmeyer, has worked on getting those updated to try to provide some of these things, quick information for mill managers, as well as some things to put up in the mill to remind employees how to optimize our quality programs. So with that, I appreciate it, and I'm happy to answer any questions.
Well, thank you, Chad. And before we get started answering questions, we would like to share a brief video. Then we'll be right back to answer the questions that were submitted during today's presentation. Organic trace minerals come in many types and formulations, leading to confusion about chemistry, terminology, and methodologies. With Balchem's Quicheur line of chelated minerals, we provide superior performance and exceptional value by keeping it simple. Binding minerals to the highest quality plant protein-derived amino acids and peptides in our world-class production facilities, using a true chelation process pioneered by Balchem and trusted in both the human and animal arenas for nearly 60 years. The Quicheur line delivers proven and consistent bioavailability to maximize performance, and a no-frills pricing approach for greater profitability. Visit balchemanh.com to see how Quicheur chelated minerals are your link to superior performance and exceptional value. As a reminder, you can still submit questions through the questions pane in the attendee control panel. But Dr. Paulk, our first question is, when considering some of the things you discussed around soybean meal, are there any major concerns with the quality of U.S. soybean meal and its value?
Yeah, so I think we are very fortunate with the quality of soybean meal we have in the U.S. And it's been very consistent. And if you look at a lot of the data that compares different countries of origins in the soybean meal, we typically see an increase in the digestible lysine concentration of that soybean meal from the U.S. So it is something we can be very comfortable with. And I think it's a great quality We haven't seen a lot of differences. Dr. Stein's done a lot of good work that shows the consistency of it as well. There have been, though, a couple of scenarios in the field where I've seen changes in performance or maybe differences in scouring of pigs when we change sources of soybean meal. And I think the interesting thing is when we look at some of these analytical techniques to measure KOH solubility or other things, we're not necessarily picking up any major concerns. They all look consistent, but the pigs are telling us a different story. So I don't know if it's, if there's something else going on. It is interesting that the issue goes away or comes back when we've changed sources of the soybean meal. So I think there is some opportunity to try to understand how we further improve our precision and formulation and really understand minor differences in some of these soybean meal sources. But some of the major issues we initially face, I think, they really have the processing figured out and have done a nice job with that. But I think we could further improve some of our components and trying to understand what's driving some of these new differences that we're seeing.
So how often do you recommend checking those incoming ingredients for quality? Every time you bring in a new load?
So I think it's one, you have to determine what your budget is for your QA analysis. You also have to think about your ingredient. The biggest thing, I think the first question to ask is what's the consistency of that ingredient and what's the variability expected with that ingredient. Anytime you have a highly variable ingredient, you're going to want to test it more to try to understand. You also have to understand what's the opportunity to capture the value there. Are you going to adjust your formulations? The biggest on soybean meal testing, the biggest value that we typically see is the opportunity to submit claims against contracts. So making sure you're paying for what you're getting can provide value back to your production system or your feed manufacturing system, and taking full advantage of that is going to help you optimize your economics. And so I think you just have to assess the variability of your ingredient, the value of that ingredient, and how you can capture that value to determine how much of your resources you want to dedicate to that quality program.
Sure. So what opportunities are there to improve precision diet formulation with soybean meal and understanding the degree of heat processing?
Yeah, so I think, the feed manufacturing system, it depends on what opportunities you have, because if we're just purchasing soybean meal and all putting it in one bin, you don't have the opportunity to really segregate it out and utilize these differences. But like I just said, I think the biggest opportunity is making sure you're taking advantage of submitting your claims if you have the resources to do that and capture that value. I think something that we're trying to figure out if it's possible, or actually how you can make it logistically possible. We're starting to see, as the data I showed you here, we're starting to see improvements in soybean varieties where they have higher amino acid concentrations, the balance of those amino acid concentrations with crystalline amino acids, how we take advantage of that in diet formulation. It's all really exciting, but the issue is the soybeans going to a processor, and then the soybean meal is all coming out from the processor. So trying to understand the logistics of how we take advantage of these improved genetic lines of soybeans and how that translates into the value of soybean meal and working that into our formulations. I think there's a lot of opportunity there, and something we'll see in the future.
Great. So this question is specifically about that high crystalline amino acid diet. You said that there was an increase in feed intake, but what do you think led to the poor feed efficiency in pigs fed the high crystalline amino acid diets?
Yeah, so we ran this study focusing on the thermal processing aspect, and I really didn't put much thought into that. And our swine nutrition team here at K-State has done research in this area, and around the same time, they had a data set come out that actually showed a very similar response, where these late nursery pigs, when you feed them high crystalline amino acid diets, there's an increase in intake and poor feed conversion ratio. And I don't think at this point we know exactly what it is. I could hypothesize there's a couple different reasons. One big discussion point is the energy value associated with soybean meal. And if we have the correct value, if we're utilizing the correct value for the net energy of soybean meal in our diet formulation. Because as you increase these crystalline amino acids, you're pulling more soybean meal out. Therefore, if you're off on your matrix values for the net energy, then that could be what's causing some of the differences in intake. There's also the whole discussion around the bioavailability, or the rate at which they're absorbed of free amino acids or crystalline amino acids versus that of soybean meal. And so, you know, there's some things to think about and try to understand what's really driving that response, but I don't think we've really narrowed it down to a clear answer at this point.
Okay. We've got a lot of questions coming in here, but I see we're at the top of the hour, so I will give you one more here. Which parameters do you consider most important for protein quality? Is this different for different raw materials?
Yeah, I think, you know, it depends on what your objectives are, and what your strategy is. Based on the data I presented today, I think if you're trying to do a direct comparison of different ingredients or maybe different suppliers, the KOH solubility is a starting point to at least give you some indication. Total lysine is also a good measurement as well. It's more expensive, but it gives you that indication. You just have to decide how conservative you want to be with your digestibility coefficients. And I'll also say never underestimate the value of physical inspection. You know, just making sure you're looking at trucks coming in, assessing odor, assessing color, all those things to give you indication if you need to do further diagnostics.
Wonderful. Well, thank you so much, Chad, and thank you everyone for attending today's webinar. If you have additional questions, and we do have quite a few that we didn't get to, but please submit them to anh.marketing@balchem.com, and we will get them to Dr. Paulk to review. The Real Science Lecture Series webinars continue on November 16th with Dr. Mike Vandehar from Michigan State University, discussing how to improve feed efficiency and how that can impact financial and environmental sustainability. Visit balchem.com/realscience for more details and to register. Balchem's podcast series continues to offer a deeper dive into our webinar topics. Tonight, we will release the last installment of our podcast focused on the new 8th revised edition of the Dairy NRC. Visit balchem.com/podcast or subscribe to the Real Science Exchange on your favorite podcast platform to listen. Don't forget to request your Real Science Exchange t-shirt. Learn how at balchem.com/podcast. On behalf of Balchem and Dr. Paulk, thank you for joining us today.